Good morning, everyone. I would like to welcome you all to our large parallel session on early warning for thresholds and tipping points in the Earth system. My name is Mercedes Bustamante from the University of Brasilia, and I am a co-convener of this session with Tim Lenton for University of Exeter. So this session will explore the methods and prospects for gaining early warning of approaching tipping points in the Earth systems. We heard a little bit about this morning. And this session will consider physical, biological tipping points elements and the human dimensions of providing useful early warning. So we are going to have a keynote presentation followed by 4 highlight presentations and then 25 minutes for discussion and questions. So I would like to welcome our presenters, Tim Lenton, University of Exeter. Please, you can come on. Winkelmann from Potsdam Institute, Germany. Marina Hirota, Federal University of Santa Catarina, Brazil. Céline Bellard, Université Paris-Sud, France. And Mark Nuttall, University of Alberta, Canada. Thank you very much. So our first presenter will be Tim Lenton. He's a professor of University of Exeter, UK, and he's going to talk about early warning of climate tipping points. So please, the floor is yours. Thank you very much.
Thanks, Mercedes. Fellow presenters, if you're more comfortable back down there, I think that's fine. We can drag you up later. So thanks for coming to our session. Well done, Ricardo, in the plenary for getting everybody's interest in tipping points, early warning. I'm going to talk a little bit about what are these possible generic early warning methods for detecting abrupt shifts in complex systems, then give some examples where we've tried to test these early warning methods for specific tipping points on paleoclimate data, in complex models, and in observational data, and then go on to the question of what should we do about this? If we see the prospect of approaching tipping points, how should it be affecting climate policy and our analysis of the climate problem? So what do we know from scientific experts, from the literature? These are some results from an elicitation process with over 50 experts led by Elmer Kriegler several years ago. A lot of complex information here where the experts were offered 3 different warming corridors into the future and gave imprecise probability ranges for the likelihood of tipping 5 different tipping elements under these different warming scenarios. But it all boils down to some fairly simple, I think, results, which is under the medium warming corridor, that's 2 to 4 degrees by 2200, you've got a most conservative lower bound probability of 16% to tip one of these 5 systems. And under the business as usual high warming corridor, and even under the most conservative assumptions, the lower bound probability is above 50%. It's at 50-60%, so more likely than not under business as usual that we should expect to see some climate tipping points. And I think that's quite at odds with what's in the past been put in economic analyses of the climate problem, where these are usually assumed to be high impact but very low probability events. So I want to talk about what are the prospects for getting early warning signals if we think there may be tipping points approaching. Of course, we would like to use our state-of-the-art models to make a forecast of where our tipping points might be, but speaking as an Earth system and climate modeler, we know our models are imperfect. So I've been interested in the possibility or the question of whether we could diagnose some useful information directly from data about the possible approach of a tipping point. So these ideas come from a well-established area of maths, dynamical systems theory. Here we've got a cartoon of a system that's in one state, but there's another stable state available, and it's being forced in a way that the state it starts in eventually reaches a tipping point here where it loses stability and the system's got to transition into the other state. The question is, what warning signals might we see before that happens? And the way to think about this is to imagine the ball moving around in this, what a physicist would call potential well or landscape. So in the climate system, we've got internal variability, short-term variability. You can think of it almost like the weather as like a stochastic noise process that's nudging the board all the time. And if it's in a very stable configuration, the climate system should be, or a part of the climate system should recover quickly from fluctuations, but as it approaches the tipping point, it will recover more slowly from natural fluctuations. It may also exhibit greater variability, greater variance, because it's moving around in this less resilient space. But to see this more clearly, I'll show you a little movie of this cartoon where we're going to look at a possible early warnings indicator. So if you want to pick up the idea that a system is slowing down in response to fluctuations, there's a simple way to measure that statistically. You just look at a time series of data from the system and look at what's called lag 1 autocorrelation. It just means how similar is one time point to the previous one. If a system is slowing down, it becomes more self-similar in time. Today becomes more like yesterday, tomorrow becomes more like today. So let's have a look at the movie. We've got, here we're going to force this system in the top left to pass a tipping point. The system's being nudged around by a stochastic noise here of a fixed amplitude. We plot out the position in the x-axis, that becomes the y-axis over here in time. Here we remove any trend in the data, look at the residual fluctuations, and then plot this autocorrelation in this sliding window on the time series. And the theory says this should go up. We should be able to visually see the system slowing down, and I think you can see that up here. And sure enough, we can measure that with the autocorrelation and see it rising in red pretty robustly before the tipping point there. The system's gone. So hopefully that conveys one simple idea of one of these simple metrics for early warning. And the other one I mentioned was that the variance should go up in the system, and it does in this nice cartoon example. Let's have a look at some tests on real data. We've done quite a few studies on this. This is just one of our results where we were looking at was there early warning signals before the abrupt exit at the end of the Younger Dryas here, as recorded in a Greenland ice core. It's kind of the final exit from the last ice age as recorded in Greenland. So there's a very abrupt transition at 11,700 years ago at the end of the time series at the top, which I've cut out. And we try and take out the trends in the data, just look at the residual fluctuations in the middle, the so-called detrended data there. You can see by eye that there's some slowing down in the climate dynamics before the final end of the ice age. You see these multi-centennial fluctuations that weren't there before, quite long-lived fluctuations in climate variability that are in an interval called the Bolling-Adderod. There are some issues with detrending the data here, but the measure at the bottom, the autocorrelation in the data, is, even though it's got a slightly erroneous jump in it, that's definitely robustly going up, and we've done all sorts of statistical tests on that. So there was slowing down in climate dynamics before this particular abrupt shift at the end of the last ice age. We've also been looking in model worlds, and this is an example where we look in a coupled ocean-atmosphere general circulation model. Admittedly, it would be seen as quite low resolution by today's standards. It's the famous model. It's a version of the Hadley Center's HAD-CM3 model. But in a model world like this, we can play experiments where here we're going to add fresh water to the northernmost Atlantic until we tip a collapse or a reorganization of the Atlantic's meridional overturning circulation. And we can look in the model world to see where the best early warning signals are, and we can ask ourselves where we're currently monitoring the Atlantic overturning at 26 degrees north here. Is that the best place to be looking for an early warning signal? So up on the right, we've got what's happening in the model world at 26 degrees north. Here's the forced eventual collapse of the overturning circulation. Here are the fluctuations in the strength of the overturning before the collapse. I think you can just about see by eye that there's slowing down in the fluctuations of the Atlantic Ocean in the model there. That's picked up here by this rising autocorrelation in time in the data. There's also some upward trend in variability. So it happens in this model world that isn't a bad place to be looking for the early warning signals of a collapse of the overturning. We can look more carefully at that. So now we look at how good are the early warning signals as a function of latitude, where good is downwards. because here we're doing a statistical test against a null model, which is like 10,000 realizations of a null model, and asking whether the signals we see in the actual forced collapse of the circulation, whether the warning signals are statistically significant compared to the null model. And the dotted line would be the classic P is 0.05 level. The black dot's 26 degrees north, where there's monitoring of the overturning at the moment. The red dots and the blue one are places where there are currently programs underway to install monitoring systems for the Atlantic overturning circulation at the northern and southern boundaries of the basin. It turns out that 26 north does give statistically good warning signals, but even better warning signals are available, if you like, in the model world if you go to the high northern or the southern boundaries of the Atlantic, which is where, incidentally, there are plans to monitor the system. That's where you'd get, in this model, the best warning signals of collapse of the overturning. You can also ask, well, how early is the early warning in the model world? So here we plot it going red when the warning signals become significant against the null model at the 0.05 level, and times on the x-axis and latitude on the y-axis. And we look at the warning from autocorrelation or from rising variance. And the good news here is the early warning signal is 200 years before this slowly forced collapse of the overturning in this model world. That's encouraging. The bad news is you need to monitor the system for about 500 years beforehand. You need to be monitoring the system at its own timescale, and that's the slow timescale of the ocean overturning, which in reality would mean we need quite high resolution paleodata reconstruction of fluctuations in the Atlantic overturning. But many of my colleagues, some of you in the room, are working on exactly that. So I don't think it's out of bounds that this could be done in reality. So let's turn to observational data. This is a map of are there trends slowing down in red or speeding up in blue in fluctuations of sea surface temperature data from the Hadley's Center HAD-ISST data set? Well, there are large areas of the ocean where there's slowing down in sea surface temperature fluctuations. There's also some areas in blue where there's speeding up. Among the areas where there's slowing down in the fluctuations of sea surface temperature is the North Pacific. And when we looked at a specific well-known climate index, the Pacific Decadal Oscillation Index, that shows an incredibly robust slowing down of fluctuations. So this index is constructed from the sea surface temperature data and the pattern thereof in the North Pacific. There's also some upward trend in variance, but then it falls off again. But there's definitely slowing down in North Pacific surface ocean temperature fluctuations. And this is a region where we know there have been abrupt shifts in marine ecosystems. And there's a story here that even if the slowing down in the ocean can be simply physically explained, in this case it's at least partly due to the fact that observationally there's been a deepening of the mixed layer in this region, and that gives a bigger heat capacity, so any temperature fluctuation is going to decay slower. When we think about the ecosystems, well, typically, the timescale of the ocean recovering from perturbations is shorter than the ecosystem. It's sort of 6 months compared to, say, 2 years for the ecosystem. But if the ocean is slowing down, then essentially it comes closer to the timescale of the ecosystem. The ecosystems will become more correlated with the ocean variability, and they will tend to show increased variability. And we just illustrate this over on the right. So these black circles and error bars are where you force a simple model of the ocean being forced by of the ecosystem being forced by the ocean variability, the slowing down of the ocean, if you like, to the right on the x-axis. And that's the ecosystem becoming more correlated with the sea surface temperature fluctuations and exhibiting higher amplitude variability as the ocean fluctuations slow down. And if you believe that the ocean was prone to tipping points, the ecosystem, was prone to tipping points, they become more likely as the ocean that's forcing it slows down. Right, so that's enough on early warning. What are we going to do about this if we accept that there's some signs that there are tipping points out there, but because of this stochastic quality of internal variability in the climate system, we'll never be able to forecast precisely where they are. We might be able to say they become more likely as the temperature goes up. So I've been doing some work with economists where we just try to put the possibility of stochastic tipping points that are a function of temperature into a standard cost-benefit analysis of the climate problem. So whatever you think about cost-benefit analyses, it's interesting to see how the results are going to be altered if you put tipping points into what here is Bill Nordhaus's DICE model. One of the models used to assess the social cost of carbon in the US federal assessment, for which it gives an answer that it's $37 per tonne of carbon today. We've simply added the POS5 actually tipping points from the expert elicitation I showed you earlier and included a stochastic uncertainty in them. And we're going to see hopefully in the final few minutes how that changes the results. So if you're not familiar with these models, they imagine a kind of omniscient social planner who essentially chooses consumption and also a mitigation policy and essentially comes to an optimal solution, if you like, for how hard we should be mitigating and how we should be consuming. Now, how do we put the tipping points in the model? We have this somewhat stochastic, what it's called pre-trigger phase there. So we have, you imagine each tipping event, and there are 5 of them here, the Atlantic tipping, Greenland, West Antarctic ice sheet, Amazon, El Nino. They each have a different hazard rate, so that's the sort of likelihood per year, per degree of warming above pre-industrial that there will be a tipping event. But there's dice rolling going on each year in the model to see if tipping happens or not. And the dice are getting loaded by the temperature going up here. And that's that sort of dependence on temperature here in the hazard rate. These hazard rates are fairly low, these probabilities are fairly low, and they're from the expert elicitation, they're calibrated from the elicitation. If you tip a system, it then has a transition timescale which is governed by its own dynamics, so it's a long timescale for the ice sheets, it's a shorter one for the ocean, and then we have to make some guesstimate of the damages that might ensue on GDP, and nobody knows what those are, but standard studies, Nordhaus himself considers values up to 25% hit on GDP equivalent to the Great Depression. Here we're playing with numbers more like a 10% hit on world GDP, which would be equivalent to the recent recession, but permanent. And we include the interactions between tipping events from the expert elicitation. So sometimes tipping one system increases the likelihood of tipping another, loads the dice up. Sometimes it does the opposite, it loads the dice down. We're nearly there. Here are the results. So in green is the original model, Nordhaus's model, which is $37 a tonne of carbon, social cost of carbon today, relatively low emissions control, atmospheric carbon goes up in green, temperature goes up to above 3 degrees this century. In black, we've got our full model. Social cost of carbon has now jumped more than an order of magnitude to $592 in the default model per tonne of carbon at the present. The blue line is the one other thing I haven't told you about in the model. We've changed the preferences of the social planner in the model, so we put what economists recommend as standard preferences for risk preferences under this kind of stochastic uncertainty. So something called Epstein-Zinn preferences, if you know your economics here. And that's responsible for about half the effect on the social cost of carbon. And then it interacts with the tipping points to give this big increase in social cost of carbon, which is effectively saying, right, the optimal thing to do is mitigate hard now. So we see 70% emissions control immediately, ramping up to 100% emissions control by 2040, which is, in this model world, shutting down fossil fuel burning by 2040. Consequently, CO2 peaks in the 2030s. Temperature in that expected scenario stabilizes around 1.5 degrees above pre-industrial. And that has become, with the inclusion of the tipping points and the risk preferences, the apparently optimal response to this threat. I think I should wrap up. It's fun in this world to mess around. Actually, in the standard model now, on the expected trajectory, we have managed to avoid all tipping points by 2200, but here, within 10,000 runs of the model, which is the grey area, you can still find some examples where you tip several systems and they tip in different orders. So I won't dwell on this much, but there are cases where if, for example, we tip the Greenland ice sheet, this is assumed by the experts to increase the likelihood of tipping the Atlantic overturning because we're adding fresh water to the North Atlantic, and that causes the social cost of carbon to jump upwards. Suddenly there's more incentive to mitigate, to try and avoid further tipping points Other times it drops down because now we've passed a tipping point and we can no longer avoid it, so there's less incentive to mitigate. But let's wrap it up. The story is that if business as usual continues, then tipping points are expected to become high-impact, high-probability events. I've shown you that these early warning methods exist, and they've been successfully tested in the paleo data and the models, although we'll need some further work to actually get them to work in reality. The observational data is suggesting some interesting slowing down signals in the ocean, surface ocean, and that have implications for expecting increased ecosystem variability. If we took this threat seriously and put it in a standard cost-benefit analysis of the climate problems, the answer comes back that the optimal thing to do is to mitigate very hard to reduce the likelihood of these future tipping points. In fact, to set the social cost of carbon very, very high, it's gone up more than an order of magnitude from the baseline model. But of course, all of this assumes perfect rationality by an omniscient social planner, which is not, of course, the reality we live in. Thank you very much. So I'll sit next one. I'll sit next one.
Thank you very much, Tin. Our next speaker will be Winkelmann from Potsdam Institute for Climate Impact Research.
Thank you very much. I'd first like to thank the conveners for inviting me here to talk about one of the tipping elements that we just saw in Tim Lenton's talk, that is the Antarctic ice sheet. Now, I don't know, but maybe some of you have been at the sea level session yesterday. And what we know is that sea level is rising currently. We also know, and all evidence points to that sea level will continue to rise throughout the century and beyond. And if we want to think about long-term sea level rise, we really need to look at the Antarctic ice sheet. I think the Antarctic ice sheet can rightfully be called the sea level giant. As you can see here, the total sea level potential, meaning that if you take the entire ice mass and distribute it over the ocean, then this is how much sea level would rise globally. So for the West Antarctic ice sheet, which you can see here on the left, sea level would rise by 5 meters, and for the East Antarctic ice sheet, by even the tenfold, 50 meters of global sea level rise. Here you see some of the hotspots that have actually drawn our attention in the past, and in the recent past. This is the Amundsen Basin, which I will talk about, a bit more about later. The Southern Antarctic Peninsula, and also 2 regions in the Eastern Arctic ice sheet, which are the Totten Glacier and the Wilkes Basin. What they all have in common is that they might become or have become unstable. And the reason for this is the so-called marine ice sheet instability. This is a very simple mechanism, and in order to understand it, it's easiest to look at a cross-section through West Antarctica like this one. What you see here is we have our ice sheet. It's sitting on ground mainly below sea level. That's one of the very important conditions for this instability to exist. And the ice sheet is basically pushed by its own gravity towards the ocean and drains into ice shelves. And the separation, well, in this case, it's a separation point, but in reality, it's a separation line between the sheet and the shelf is the so-called grounding line. Now, if we imagine that the grounding line is somewhat pushed towards the center of the ice sheet, so land inwards, then this is what triggers the instability. We know that the flux across the grounding line is somewhat decided by the ice thickness of the ice sheet at the grounding line, meaning that if the grounding line retreats, as we can see here, towards the center, then we have a higher ice thickness. That means more ice flux, which in turn will push the grounding line further inland, which will lead to higher ice thickness, more ice flux. So this is a self-enforcing feedback that can lead to unstable retreat of the grounding line, and thereby ice loss, and thereby sea level rise. Now, as I said earlier, the tipping of the Antarctic ice sheet, or particular regions of the Antarctic ice sheet, is not just a theoretical possibility. It has become reality. The Amundsen Basin in West Antarctica has likely tipped. What you see here are the glaciers draining the Amundsen Basin in West Antarctica. They include the fastest glacier in Antarctica altogether. And as you can see, they have sped up in the recent years, especially in the past decades, has been observed for a number of years now. And now they have basically hit that point of no return where the glacier, the grounding line, has moved past that bump in the topography. So it has moved past that place where now it's on a retrograde slope, and there's basically no mountain behind that, or no hill, or nothing that can stop it until the entire basin is drained out of ice. So this will lead to global sea level rise of about 1 meter. It's still unclear how fast this can happen, but it's clear that this is going to happen, and this is why it has been called a new era of irreversible climate change. A second region that has caught our attention is the Arctic Peninsula. And there's some debate whether or not this region might also have tipped recently. And the reason you can see here, you have a comparison between the surface elevation changes in the years 2003 to 2008 and 2010 to 2014. And what you can see on the left, that was the situation sort of at the beginning of this century. And then on the right, you see all these red spots, meaning that there the surface elevation has been lowering. And there's some discussion whether this is caused by dynamic thinning or maybe through snowfall effects. But it is possible that the peninsula has tipped also, or could tip in the future, because it also fulfills these two conditions that you need for the marine ice sheet instability. So that the ice is grounded below sea level and that the bedrock is sloping land inward. In order to understand whether or not we can avoid the next tipping in Antarctica, we really need to understand the ice dynamics. And that includes changes in snowfall, it includes the effects of ocean warming, of surface warming, even though in Antarctica it's really cold, so surface melting is not an issue right now. It includes ice shelf calving and basal melting. And all of these processes take place, well, all around the Antarctic ice sheet. We've seen that the Western Arctic ice sheet has become unstable, or part of it has become unstable. We've seen that the Antarctic Peninsula might have become unstable. And there are also regions in the Eastern Arctic ice sheet. To remind you, the Eastern Arctic ice sheet altogether holds enough ice to raise global sea level by 50 meters. So we've seen that there are also regions in the Eastern Arctic ice sheet that could become unstable through the same kind of mechanism that we saw before. This is one particular region in Eastern Antarctica. It's the largest marine ice basin that's fully connected by subglacial troughs. And it is grounded below sea level, and the bedrock is sloping land inwards. So this is a candidate for the marine ice sheet instability. Currently, there's still an ice plug, we call it, so a small fraction of ice that's kind of working as a plug to hinder the ice from unstoppable retreat. You can see it in red here. It looks quite tiny on this map, and it actually is. So compared to the large mass that sits behind it, the ice plug only contains enough ice to raise global sea level by 18 millimeters. So it's really small compared to the overall volume of that region, which is enough to raise global sea level by 3 to 4 meters. So currently, the Wilkes Basin is still protected, but that might change in the future, for instance, through basal melting. And what you see here is sort of an animation of what this process might look like. So this particular simulation has only been triggered by sort of removing the ice plug, and then there was no additional outer forcing. So all that you can see here is the self-enforcement, the internal dynamics that's driving this ice loss. And as you can see, in the beginning, the ice plug is removed, so 18 millimeters sea level equivalent, and then you get self-sustained long-term sea level rise of 3 to 4 meters. Another thing that's really striking is that sea level takes a very, very long time. In this particular case, we look at timescales of tens of thousands of years. That's important to keep in mind, because it also means that we need to look at sea level in terms of commitment. And now I want to add the other sea level components to the equation that are the Greenland ice sheet, the thermal expansion, and the mountain glaciers. And we can look at the sea level commitment over the next 2,000 years for all of these components together. And we see that it's a quite linear dependence, meaning that the sea level commitment rises with 2.3 meters per degree of warming. So we can already know today what we're committing the planet to in the future in terms of sea level rise on the very long term. What does this mean? 2.3 meters per degree of warming. That, of course, affects us and future generations. More than half of the world population right now live near coastlines. And there's a lot of infrastructure and also a lot of cultural heritage that is right at the coastlines. And Anders Levermann and Ben Matsayan have shown how this kind of sea level commitment would affect the world's population, well, sort of the territories of different countries, but also the cultural heritage in the future. What you see here are all the different cultural heritage sites that would be committed at different levels of warming from 1 to 4 degrees. And in addition to that, we can look at how the territories of the countries are affected. And what's quite striking is that if we look at the habitat and the spaces that we live in right now, our current warming has already committed us to a loss of about 0.7% of the total land area. In a 3-degree world, as you can see here, this would rise up to 1.1% of land area. In a 3-degree world, 3 to 12 countries will lose half of their land territory. In the 3-degree world, 25 to 36% of the countries will lose more than 10% of their territory. And about 7% of the global population is now living in regions that in a 3-degree world would be below sea level. So 2,000 years, that sounds like a very, very long time, but we can also look at this in terms of what is happening within this century. So here you see for the 2 RCP scenarios, which I'm sure you've seen in many of the other talks, the commitment, especially for North America, for the US cities. And as you can see, in both scenarios, Miami is actually already committed at the beginning of this century through our greenhouse gas emissions and thereby the warming that follows. But there's still a striking difference between the 2 scenarios. And you can see all the cities that would be committed in the US under the different warming scenarios. Just to remind you, RCP 2.6 would lead to a warming that stays below 2 degrees. RCP 8.5, the business as usual, would lead to about 5 degrees of warming. And under these 5 degrees of warming, New York City would also, which you see at the very end of that red line, would also be committed. This has been picked up quite a lot, including by Barack Obama. And I just think it's important to also think about these long-term changes and to think of sea level rise in terms of commitment. Thank you very much.
Thank you very much, Ricarda. Now moving to terrestrial ecosystems, I would like to call Marina Hirota from Federal University of Santa Catarina, Brazil.
Good morning, everyone. First of all, I'd like to thank Mercedes and team for organizing such a nice session and for inviting me to be here today to speak to you. So I'd like to start by presenting you some of the boundaries I'm going to talk about today. So first, in here, you have the Cerrados in Brazil, which contains savanna biomes, or savanna physiognomies, and the forest, the tropical forest, in this case, the Amazon. And in here, another example I'm going to give you is related to the drylands, tropical drylands in South America. So I framed the title of this presentation as, Are There Tipping Points in Terrestrial Ecosystems? Just because I think we still need to go a step forward to understand better the system before ensuring that these tipping points are there. So I'm guiding you through this presentation using a conceptual idea that my colleagues have already presented a bit, and then show you some evidences and caveats on terrestrial ecosystems, And then finally, to see or to show you the implications for climate change and land use change. So the conceptual idea behind the tipping points, and I think this is important, is to define an ecosystem state here and the conditions in which this ecosystem state can exist. So in here you have, for example, in this part, a dense woody cover, which can be a boreal forest, a more vegetated state in the drylands and the Amazon forest. And in here you would have less dense woody cover, meaning the savannas, this very lonely tree in a dryland, or the tundra. So in this sense, those 2 points here are the tipping points in which the system could collapse by reaching it to the downwards, I mean. And then, oops, sorry. And then to go back here, you would need to reach another tipping point, which is not the same, to go back. So this is very concerning regarding to climate change, because imagine that the system is forced here downwards, and then if it reaches the tipping point, it can irreversible go down here and take a long time to recover, if it's the case. So as conditions, we can point climate, soils, fire, for example, topography, and the fauna driving the ecosystem. And as the ecosystem state, we can name the percentage of tree cover, or for example, the photosynthetic activity of vegetation. So by this, I mean, we need to identify interactions, synergisms, feedback mechanisms in which this flip could occur. So it's not just a matter of one value in temperature, but also the interactions in the systems. And this includes temporal scales, spatial scales, and they're different, and they have interactions between them. So modeling studies have already assessed these interactions, but in fact, I think the importance of observations in this sense has not been shown that much yet. So in this context, I think the first caveat is to have long time series enough to see these flips. And it's not very usual to find this long time series yet. Right, so it's difficult to say, oh, okay, it's going to flip, but I have never seen something like that yet, so it can be a problem. So I'm going to give you one example in tropical drylands, and this is, the credits for this are Milena Holmgrens and her colleagues. And then this spot here with a very lonely tree in northern Peru has been colonized by recruiting trees during a very intense El Niño event from 1907 to 98. And this happened because these soils are very sandy, or the percentage of sand is very high, and the water percolates very fast after a very strong El Niño event, which causes lots of rain, so 300 millimeters to 2,500 millimeters a year. And then this water, because the water table is very shallow, plants can escape the dryness by going down and accessing this water that has been stored in the water table. And on the other hand, it can escape herbivory by achieving an enough height to grow and escape herbivory. So these mechanisms allowed this ENSO event to recruit and reforest this area here. So it's possible to see that in a very short scale. But regarding to the long time sales, for example, in a tipping element like the Amazon forest, we still don't have long enough time series to assess the impacts like in depth. So what we do, we sort of cheat the system, and we get a continue between grasslands and forests to assess the evolution of the vegetation in the case you had a time series, a long time series. So from grasslands, it could be recruited, or plants could be recruited, and you would have a savanna, and then a forest, for example. So in this sense, we could, well, we did get the tree cover percentage from a satellite sensor, MODIS, and it's a snapshot in time, so remembering that we have this continuum here. And the way we see these tipping points, or alternative states, is this. We just plot the frequency distribution of tree cover. And then we would have these peaks here. So it's a very roughly measurement of a treeless state, a savanna state, and a forest state. And by this, we mean that these are preferable places where vegetations are, or vegetation is. Sorry. So when we do that, we can also analyze the data using the conditions here, and by conditions we get mean annual precipitation, and as the ecosystem state, tree cover percentage. And then by this graph here, we see something like that. Well, you may not see that, but when you put in colors like this, you can see that the shape is slightly like this, right? So to prove that, you can use a mathematical procedure, and then I will refer to what Tim showed previously. And in here, we would have like a valley showing the forest preferable state, and in here, the savanna preferable state, and the treeless preferable state, with the white dots like unstable states, meaning that you are in this zone here, in which you could flip towards down or towards up. Right. And what about the other conditions? Mean annual precipitation is not the only one driving the system. So accounting for dry season length, so just taking points with dry season length with less than 7 months, and intermediate mean annual precipitation between 1,000 and 2,500. And accounting also for fire occurrence, we can see here the same histograms, and in here are the histograms without fire, and this one with fire. So we see that the preferable state is not anymore like a forest in Africa, but it would shift to a savanna because of fires. In Australia, there was not enough data to do the entire analysis. And then in here for South America, we flipped from a forest state to a forest and a savanna state because of fires, giving the dry season length, which means seasonality in climate, and this intermediate rainfall range. So looking at this, at the global distribution, we could see that, and I would point out the orange here and the light green, as places where you have bistable possibilities. Currently, these orange ones here, they are bistable and classified as savannas. And the light greens, they're bistable and classified as forests. So you can see in the Amazon here that you could flip towards a low woody cover physiognomy in the face of drivers such as climate change and land use change. But then, that's a point where a mathematician has to go into ecology a lot. What happens is that you have caveats. First of all, remote sensing data is likely to carry a lot of uncertainties, right? So we have to be very cautious in assuming catastrophic shifts using this. And then when you use it, you have to use also field data and field observations to assess the possible impacts. The second thing is that it's difficult to really construct a global model because the differences among continents are very high. So for example, in a conceptual model here, including all those elements, fire, soil, and climate, you can see, and maybe it's not totally visible for you, but I want to highlight the arrows and how bold they are. So you see that in Africa, some of the connections are much stronger than in South America, and so they are in Australia. And in some of them, they are not significant at all. So it's very difficult to assess tipping points in a global scale without really assessing what you have downwards in more finer scales. Right. What seems a consensus, though, is that in this grassland savannas and tropical forest continuum, you would have a lower threshold here in mean annual precipitation in which woody cover would be limited by water supply only. And then you have a more stochastic range here where fire, with its stochastic nature, would have a role in the system. And then in here, from this, you would form a canopy or a close enough canopy to have or to diminish the fires, and then you wouldn't be affected anymore because your microclimate would be too humid, too wet. So I'm going to focus here on the fire regime and finish because I'm running out of time, sorry. And then this bistability here is, oops, it's not moving. Thank you. Yeah, but then some authors have assessed these thresholds in a local scale, and it seems for South America, for example, that this range goes from 800 and 2500 to have a closed canopy formation, and oops, it's not going anymore. Okay, and then the fire thresholds are divided in two. First, you have a threshold related to individual plants, and it's related to the bark thickness that the trees have to cope with frequent fires and intense fires. And you have the fire suppression threshold at the community level in order to have canopy closure. So in terms of climate change and land use change, if you increase the frequency and intensity of extreme climate events, and if fire regimes become more and more intense with anthropogenic sources, and accounting for deforestation and cropland establishment, you would have something like that. The system can be pushed towards another state, an alternative state, or it can erode the basing of attraction and you lose resilience, and a very simple drought event or very simple wet event could trigger the system to a different alternative states. So summarizing this, there are evidences for tipping points, particularly for the Amazon basin, and they are there, but we have to be very careful because we still need to understand the responses in terms of functioning of the ecosystems to assess the impacts of climate change and land use change. It's possible that these two external forces, they push the systems toward a different equilibrium, but they still need investigation of the feedbacks. Thank you very much.
Thank you, Marina. Our next speaker is Céline Bellard from Université Paris-Sud, France. And she's going to present about the effects of climate change and other drivers of global change on biodiversity.
So good morning, everyone. So I will talk to you about the effect of climate change and other drivers of global changes on biodiversity. So, as you must know, the number of extinction largely increased over the last centuries, in particular for vertebrates like mammals, birds, reptiles, amphibians, fishes, and even a lot of invertebrates go extinct. And most of these extinction rates are largely below the background rate from fossil records. And in fact, these extinctions are mainly due to the combination of human actions And one of the most important drivers of biodiversity loss is habitat loss. Biological invasion, which represents the second most important drivers of biodiversity loss at a global scale. In particular, many native species from highland have been extinct due to the introduction of new predators by humans. Overexploitation and more generally biological resource use is also one of the most important drivers of biodiversity loss, and probably climate change is going to be one of the most important drivers of biodiversity in the next decades. And in fact, all of these drivers increase the pressures on existing biodiversity and ecosystems that might lead this ecosystem to tipping point, at which the ecosystem shifts to less productive state, from which it may never recover. So the challenge here, for me at least, it was to try to identify and quantify the increasing pressure that biodiversity might suffer in the future. So to do that, many scientists that work on impact on biodiversity from climate change use statistical correlative models. The basic idea is to correlate the presence of the species at the global scale with some environmental variables like temperature, precipitation. And using that relationship, we extrapolate in the future where might be the suitable condition from the future. So using the climate change variables or land use changes. So I would like to show you an example when we use that methodology to evaluate the effect of climate change and land use changes on invasive species distribution. So to do that, we have calculated here for each of the pixels at the global scale the number of invasive species that might find suitable conditions in the future due to the changes in climate and land use. And in red, we have this area where we will have an increase of the number of invasive species in the future, so an increase in the pressure for biodiversity. And in green, we have the areas where we have less number of invasive species that are predicted to occur in those areas, because the condition will be less suitable for those species. So these results are important because it allows us to establish where the increasing pressure and decreasing pressure will occur in the future because of these invasive species. But, to my opinion, they suffer from two main issues. First, they focus on the effect on one driver on the others. And as I told you at the beginning of this talk, many of the extinctions have been due to the combination of multiple factors. And for now, it's really difficult to evaluate in the future the combined action of these multiple factors. And the second main issue is now we do not account for the impact on those drivers on biodiversity. In fact, it's mainly an exposure of the areas and on the biodiversity to these factors of threat. But we don't establish if the biodiversity will be more or less vulnerable to these threats. So to try to take into account these two main issues, we use and develop a cumulative impact index at the US scale for biodiversity. So here we have evaluated 4 different threats: invasive species, sea level rise, climate change, and some land use changes. And we have also taken into account the proportion of species that are vulnerable to these different threats. So to do that, we use the IUCN database, so International Union for Conservation of Nature. For each of the species that have been evaluated, we have the information about which threat is associated with the extinction risk of those species. So we use that information to establish in the future if the species will be or will not be vulnerable and exposed to this threat. So first, we have evaluated the individual threat distribution over US. So we have evaluated the climate change exposure over US. We found that most of the climate change will occur in the eastern part, but also in some areas over the western part. While land use changes will mainly occur in the central part of the US, and biological invasion is more restricted to the eastern part. So if we combine these 4 different threats, 4 different groups of threats, we found that on average there is 1.5 threats per pixel. So it means that clearly this threat will occur simultaneously over US, and in particular most of the eastern US will be affected by multiple threats simultaneously. So this doesn't mean that this threat will have the same impact at the same moment, because there is a time lag between different threats, but they will occur probably at the same time. Maybe the impact will be delayed. So now the question is, if we take into account the proportion of species that might be vulnerable to this threat, do we will have the same pattern? And in fact, for amphibians, for example, we found a slightly different pattern. So we found most of the eastern parts have high cumulative impact value. So it means that invasive species, climate change will occur in these areas, and on top of that, we have some species that are particularly vulnerable to these different threats in these areas. But also, in the central part, we found that there is a high number of species that are really vulnerable to some land use classes. So it means that just looking at the exposure of different threats, we might forget this part of US that might be of high concern for the protection of amphibians. And here we were able to highlight these areas. Now, regarding mammals, we found also that most of the eastern part have a high cumulative impact value that are mainly due to the invasive species climate change, but also to some species that are vulnerable to develop and disturb areas that will occur in this part. Regarding reptiles, we found the larger areas of high cumulative impact value, and also over the western coast of US, that are mainly due to a combination of a higher number of threats compared to the other groups. And regarding birds, we also found some areas of high cumulative impact value over the western part of US that are also due to a combination of different threats. So if we summarize the cumulative impact value for all the different taxa, we found that this spatial pattern is due to a combination of invasive species, followed by climate change and change of land use to cropland and pasture, that all showed broad positive correlation with cumulative impact value across the different taxa. So the key message here is really to consider multiple threats, because they are likely to occur simultaneously. And second, we need to consider the vulnerability of species that are vulnerable to these different threats, because the response and the information for conservation will not be the same. So, in conclusion, here we use USA to illustrate the need to consider multiple interactions between climate change and other threats on biodiversity, because climate change will not occur alone. Biodiversity is already under multiple threats, and we need to consider that, especially because identifying the increasing pressure on biodiversity will help us to identify where we will cross the tipping point for the ecosystems. So now the question is how we can remain in the safe operating space here before going through a tipping point. Well, we need to increase the resilience of species and communities to multiple threats. And one way to do that is to increase connectivity, first between protected habitats. And a possibility is to identify the analog climate corridors, so corridors where species might go through, where the climate condition will be suitable for them, and that will be stable in the future. And second, we need for global rather than regional or national targets for species or habitat protection, because many of the protected areas that have been established in the past are currently disconnected from each other, and this will be a main issue in the context of climate change. And finally, to my opinion, one of the main knowledge of my field is first, we fail to consider the nonlinear response of species to threat. For now, we consider that the intensity of the threat will be correlated to the species respond to the same threat. We know that some species are able to adapt to this threat, and we fail to consider at a global scale, at least, how the species will respond to this different threat, taking into account the adaptation potential of those species. And second, we fail to consider the context dependence of this threat. So now we consider mainly the exposure of this threat for an ecosystem, but an ecosystem that is intact from multiple threats or an ecosystem that is already under multiple threat will not react in the same way from the climate change issue. So we need to take that into account. And finally, we need to move forward multi-scale studies that goes from species to community to ecosystem services in the context of climate change and from a conservation perspective. So I would like to thank Tim and Mercedes for their invitation and also you for your attention. Thanks.
Thank you very much, Céline. Our next speaker is Mark Nuttall from University of Alberta, Canada. And going to hear about approaching tipping points, context, anticipation, and community-based monitoring.
Thank you very much, and also thank you very much for the kind invitation to come and present. So I'm a social anthropologist, and I'm going to talk about a few aspects related to societies when we try to talk about tipping points or tipping elements. And I'm going to talk a little bit about some of the work that I do in Greenland, because I want to talk a little bit about scales, but I'm going to do this by way of illustrating some of the work at a local level. So one of the underlining ideas, I suppose, of this session was to think about the kinds of methods we could devise in terms of identifying tipping elements and tipping points. And I suppose if we are approaching tipping points, and even if we can't avoid them, one of the important things for societies and communities is to have enough information about the changes that are about to occur, so that they can anticipate some of these changes and devise ways of thinking about what to do when confronted with them. So when we talk about scale, we hear a lot about ice caps and ice sheets approaching tipping points, and of course in Greenland there's a lot of information out there about the possibility of the Greenland inland ice approaching a number of tipping points has already been discussed. But when we're talking about how we can identify tipping elements, I think it might be useful when we think about interdisciplinary work to think about the scale. And this might be possible at a local scale when we work with communities. And I've worked in Greenland for a number of years, but more recently I've been involved in an EU-funded project, ICE-ARC, Ice Climates and Economics, the Arctic Region in Change, where we work in the far north of Greenland, in the northwest, in the areas of Upernavik and the Thule area in the northwest. We work very closely with communities. We have a multidisciplinary dimension to this project where we have oceanographers, anthropologists, and importantly, we have community research partners. And in this part of northern Greenland where sea ice is present for 6 or 7 months of the year, and sea ice is fundamentally important to the livelihoods of people who live in the far north of Greenland, they notice some rather dramatic changes. But also when we think about whether the kind of sea ice ecosystem is also approaching a tipping point, how we incorporate the local knowledge of the people who live on the ice, who depend upon it, who utilize it, and who think about it in a multitude of different ways is crucially important. And we begin to look at how local knowledge can inform some of the science that's being done. So hunters, for example, have to sort of have this incredible understanding of the sea ice and to be attentive to the minutest of details, whether it's to do with the color and the texture of the sea ice, the slush on the surface, or whether they're looking at the changes that occur during breakup and even the open water season, and then the formation of sea ice again. And so we're working with hunters to chronicle this knowledge about sea ice, which is of fundamental importance to us. So what we're trying to do is set up a long-term project, in a sense, that we can sort of build a community-based monitoring program. And this slide, for example, which was taken a year ago, but is at the ice edge and I was just also recently at the ice edge in northwest Greenland, and over the years I've seen myself some of the dramatic changes that have occurred. And whereas about 15 years ago it might take in May, June about 7.5 hours to have dog sledged out to the ice edge, now it's around about 2 to 2.5 hours. So is this evidence of a tipping point? Well, we don't know yet, but there's certainly some considerable and dramatic changes that occur and that people are observing and experiencing. And this has a fundamental significance, of course, to the socio-economic everyday context of the communities in northwest Greenland. So incorporating local and scientific knowledge is, I think, an important first step when we think about the kind of interdisciplinary methodologies, when we look at tipping points. Mapping the changes, mapping the local areas where people see the kind of the most apparent changes, building up a kind of database, but also one of the important things is building capacity within communities so that people become researchers themselves. And as part of the ICEARC project, one of my colleagues, Stefan Olsen, and his colleagues from the Danish Meteorological Institute have been working with hunters in terms of going out onto the ice in the winter, at the beginning of spring, to measure the ice thickness, but also to measure the water column. And part of the project next year will work with the hunters where sensors will be placed on the runners of the sleds. And so over several months, you have the local community themselves actually doing the kinds of research that's important. And they want the material, they want the data, they want the scientific understanding. And what's very important is to, as I say, build this capacity for a kind of long-term community-based monitoring program, but also to have regular involvement between the scientists and the communities in terms of what that data actually is and what it's useful for, rather than just giving back scientific knowledge. So we sit down and we actually sort of have long conversations about what this means, how it can be used, how it can be thought about, and how it can be improved upon as well. Another aspect of the program is to take sediment cores from the bottom of the fjord. And this is an interesting aspect of the project too, because here we begin to get into quite interesting conversations about what different groups of people or stakeholders, whether they're scientists or local communities, actually think about and understand by the term tipping point. So whereas for a scientist, an oceanographer, getting a sediment profile of a fjord system might be important because it can build a coarse topographic map that has information about the glacial history of the fjord, for the local communities, this becomes important because it gives them information that they can combine with their local understanding of the fjord system to help them think about things like fisheries and the best places to go and fish. I want to talk a little bit about the importance of understanding tipping points and climate change more generally within a broader context. Now, in the communities in which I work, when we talk about climate change, and even when people talk about the astonishing changes in the ice that they see around them, they don't always necessarily think about climate change as the most immediate thing that affects their lives. Quite often people say, well, you know, the environment has changed in dramatic fashion in the past. We've got around it. We've negotiated this. And when we look at the kind of cultural dimensions of understanding the environment and what human-environment relations are, we try to build up quite a rich picture of how people think about the world around them. Now, in the Greenlandic language, the word for nature or environment is a word, it's called pingotitak. And when you literally translate that, it means a place of becoming, happenstance. And so the world around people is constantly undergoing a process of change and becoming. So glacial retreat, glacial surging, diminishing sea ice, this has all happened in the past. This is not to say it's not something that people are not alarmed about. But when people talk about tipping points and when we talk about the kinds of ways we can translate these terms into indigenous languages, people in the communities in northwest Greenland often say, well, a tipping point in the ecosystem isn't really what we're necessarily worried about. But we've also approached and passed several tipping points in our social environment before, which have affected us in far more dramatic ways. And one of the things that people still today talk about, for example, as a way of trying to understand some of these changes, or what happened in the 1980s when environmentalist organizations and animal rights groups campaigned very successfully against Inuit seal hunting, which more or less then killed any kind of market in sealskins, led to the European Union Sealskin Directive, which prohibited the importation of sealskins. And when people talk about these things and they sit down and talk about the changes in the environment around them, they often say, well, whatever is going to happen in the climate, it's not going to have perhaps as far-reaching an impact as, for example, the conservationist groups and the animal rights groups did in the 1980s to our lives and our communities. And these are legacies which are still very present today in many communities. So understanding these kinds of effects, these kinds of changes that already happened in small communities, as well as other rather profound social and economic changes, are really important when we try to understand climate change and also try to understand tipping elements and tipping points. Now, going back to what I mentioned just before about measuring the thickness of sea ice, for example. In our project, when the scientists, my science colleagues, look at the changes in the thickness of sea ice in the fjord systems, for example, in the Qaanaaq area in northwest Greenland in the last 15, 20 years, the science shows us that the thickness of the sea ice on average has reduced from 2 meters to about 98 centimeters. So from a scientific point of view, from an academic point of view, we might see that as evidence of quite dramatic change, and perhaps even as evidence of an approaching tipping point. From the point of view of the community, this is not met with shock and horror. People say, fantastic, it's thinner. It means we can drill down into the ice, through the ice, to reach the halibut that we can now fish for, that can contribute to the good fortune of our community. So it's an opportunity as well. So understanding the past transitions, understanding movement, forced location, and so on, and rapid socioeconomic change is quite significant. In our work, we also look at other kinds of drivers of change. So when people talk to us about what they see, they also talk about the changing migration routes of fish and of animals such as narwhals. Now, we could take the movement of narwhals as an indication of some of the shifts in the environment, the changes in sea ice and so on. But this is all happening within a broader context of other things such as oil exploration. And the map on the left shows the seismic exploration activities that have taken place in northwest Greenland over the last 15 to 20 years or so. So when we look at narwhals as a possible indicator species of climatic shifts and regime shifts, we also have to try and disentangle a lot of other factors. It's far from certain how far the seismic activities, what kind of impacts they're having on narwhal movements, but we're involved in another project right now which we're trying to understand this. Narwhals are acutely sensitive to noise, but they're also acutely sensitive to changes in sea ice. So when hunters tell us that they've noticed dramatic changes in the migration movements and the routes of narwhals, is this to do with the changes in sea ice? Is this to do with the changes that have arisen because of the noise, perhaps from seismic activities? So all these are some of the aspects that we're also trying to look at and understand. At the same time, when new economic opportunities affect people and bring new kinds of possibilities, such as the emerging halibut fishery in the far northwest of Greenland, again, the changing climate means these economic possibilities. And if we tie this back to the difficulties of actually, and the realities of hunting in the modern world today, and the difficulties of making a living, the halibut fishery, for example, is an economic boom. People are very excited about the prospects of finally there being some kind of economic possibility of living a good life in the Northwest. So climate change is seen as a positive thing in some ways by many people. The tipping point might come, however, if the biological evidence that's perhaps going to inform government decision-making about quota systems affects the development of the Greenland halibut fishery. So when we talk to people and we go out with people and we live with people and we travel with them on the ice, they don't talk about climate change. They talk about quota systems, resource management, regulations, and so on, and say that these are the real kind of concerns they have that could tip their societies into some kind of other state. Thank you.
Thank you very much, Mark. We have now time for questions. There is one question there. Maybe we can collect 3 questions at a time, or just, okay.
Thank you very much for your nice overview on early warning. I would like to issue a word of warning on early warning, because early warning might work in rather homogeneous systems like the Lenton volcanic circulation, big ice sheets, but in a heterogeneous landscape like, for example, Africa, we find a situation that tipping might not emerge from the loss of a local stability, but might be induced from other regions. So we are not detect this early warning methods using data. We can use perhaps the early warning method to detect the hotspots, causes problem, but also early. So I'm not sure how to take it into account, but that's another uncertainty challenge.
Absolutely, Martin. Yep. And I think Sebastian Battiane's thesis work was very good on that. But there are, as you know, there are people also working on using spatial correlation and other spatial indicators as possible early warning signals. The simple idea would be for some complex, spatially extended complex systems approaching a tipping point, they become more, different points in space become more correlated with each other. So you become more correlated with neighboring points. And although that won't always work either, that's showing some promise for these spatial situations. So I'm really just offering some suggestions of ways into what we can all appreciate as a complex problem where very simple methods aren't always going to work. But the good news is there's a massive body of work on how to analyze nonlinearities in complex systems, mostly developed in physics. And I think the more we sort of delve into that and try and bring it over to our field, the more we might learn.
Could you please use your microphone, please?
Oh, je m'excuse. I'm interested in vulnerability, and with all of the stakeholders that you deal with, I find that people who don't think they're vulnerable aren't interested in adapting. And so to see that people in the far Arctic, the far north, might not feel particularly vulnerable to climate change, I wonder with the stakeholders you deal with from each of you for funding, and also, you know, in terms of their own relationship to your particular areas, do you find that there's a real need for them to be vulnerable or to feel vulnerable to see a tipping point as even being relevant?
Maybe Mark could address it.
Yeah, Mark, why don't you start?
Yeah.
Could you just repeat the last bit, because it was difficult to hear you. Yeah, sorry.
So do you find that there needs to be some sense of vulnerability to climate change before anyone's going to be actually even interested in whether or not a tipping point might be relevant to them?
Okay, thank you, yes. No, I don't think so. I mean, that's not to generalize, but certainly not in the north. But there are different contexts. So if we look at the Arctic, circumpolar world more generally, in the Canadian Arctic, there's more of a political discourse where northern communities are seen as quite highly vulnerable, and also where the human rights aspect of climate change is stressed quite considerably. In the Greenlandic context, there is a rejection of that, where people quite stridently say, well, we don't want to see ourselves as victims to climate change or to be vulnerable to that, in a sense. But I think it's people that are aware of different kinds of changes that take place. And here we get into incredibly, different kinds of sensitive issues where people in northern communities say, well, there are more people killing themselves than are being affected by climate change. So when people talk about being vulnerable, they talk about other kinds of social changes that affect their lives or other kinds of issues that affect their lives, health and so on. And it's not to say that climate change is not thought about as in that way. I think it merely magnifies the existing changes that affect people.
Thank you.
Yes, thank you very much for most valuable presentations. Could I just pick up on the recent science coming out of the impacts on Antarctica? And you actually touched upon it with a great clarity. And I think I wrote down clearly, you said 2.3 meters per decade of 2.3 meters per decade of warming will give us in terms of committed sea level rise. And that's a profound threat consideration.
I'm sorry, that must have been a misunderstanding. So it's 2.3 meters per degree of warming.
Yes, for every degree, indeed, yes. Well, but that is still a profound concern, isn't it? And how do we capture that reality or that threat and feed it into policy? Because if we're still talking a lot about 2 degrees as the kind of level we're all kind of corralling around, and it's certainly out there in policy, that's a lot of committed sea level rise. It may take a while to be realized, of course, but my goodness, how do we in this room address the issue of getting it out there in terms of it informs policy? Because that's a profound threat, both to coastal communities, to ocean dynamics, all kinds of ramifications. Please try and answer that question.
It's a very difficult but also very important question. So I think that really this sort of hints to the greatest challenge that we have with tipping points in the Earth system. And that problem is something that Mark also pointed out. It's a problem of scales. So it's a problem of spatial scales, but also of time scales. And yes, how do you communicate that there is something like a commitment, meaning that the changes that we force on the climate system or on the Earth system today will have impacts over 2,000 of years or even longer. Sea level rise is one of those really striking examples where most of the change, the bulk of the change, actually happens after a long time. So how do you, it's a really difficult and like I said, it's a great challenge to communicate that what we're doing right now, the emissions that we're producing right now will have impacts so far into the future. So yes, I agree with you. It's a great challenge.
Just a quick response, Paul. As someone from the city of Exeter, well established in the Roman occupation of Britain, so been around for more than 1,000 years, what I've been doing with citizens is we've been taking a guided walk through the city where we talked about the flooding prospects and the long-term view, but we walked past the cathedral and places that had been there for 1,000 years. And so we literally talked it through together on a journey around our home city, where we're also threatened, incidentally, by flooding events coming downstream the River Exe and the floodplain. So we've been able to make it real, working with artists there. We then constructed an art installation, which was a sort of a vision for a future Exeter that was partly cognizant of this changing climate background. So I think you have to bring it down. There are many ways to do this in many different social contexts, but that's what we have to do.
I have 2 questions over there, then one question here.
Yeah, my name is Stefan Ramsdorff. I want to comment on the question of how to inform policy and mention that there, of course, is a formal process for this. We have the UNFCCC COP in Paris here later this year, and to prepare this, there was a structured expert dialogue. The report has been published recently on the question whether 2 degrees is an adequate limit, and the expert dialogue actually strongly recommended to limit at 1.5 degree global warming because of those concerns, which fits in nicely with what Tim presented as an economic analysis. When you take into account the tipping points, you come to the conclusion really warming needs to be limited to a maximum of 1.5 rather than 2 degrees, which is within the range currently being discussed for the COP.
Okay, thank you. Yes, and then here.
Yes, hello, my name's Olga Raffa from climatechangesense.org, and I represent a large group of people who are wondering why programs such as weather modification and ongoing geoengineering programs throughout the world have not been taken into consideration with a lot of the research done. And we notice on a daily basis that our environment is being tipped through the aerosols being dumped into the atmosphere, blocking our sun, and there seems to be a lot of aluminium in the environment. Within the bees now have aluminium, and it's destroying their, well, there is a bee collapse, obviously, with the insects and the biodiversity. Aluminium are found in Wales. Also, we recognize that this is a military program, and the EMFs, so you've got your cell towers, your HAARP, High Auroral Atmospheric Research, which is putting heat into the atmosphere, into the ionosphere, and seems to be moving the jet streams. Have you done any research and published on the tipping points that this is doing and will cause in the future?
Okay, thank you. Tim.
Thank you.
Not precisely on those interventions, but I'm someone who's obviously worked on tipping points and also on trying to evaluate these, well, I would think of them more as existing proposals for geoengineering interventions, either in the camp of sunlight reflection methods or large-scale carbon removal methods. I've been on my own journey with my thinking about that, but as I've said publicly and in the literature, I'm now of the view that the risks posed by large-scale attempts to reflect sunlight back to space far outweigh the potential benefits in terms of reducing risk of higher temperatures and associated tipping points. So I still feel that there's a space for, and there's a need, in fact, to look at the options for carbon removal, as I think we may need that later this century, but that's not what you're most concerned about.
Thank you, Tim.
Thank you.
Hi, I'm Bart Kruid. I have actually two questions, one to Tim Lenton and one to Marina. To Tim, to what extent do you think, and in which cases do you think that there will be enough time in designing an early warning system to actually detect the necessary statistics before the tipping actually happens? To Marina, a very different question. What you're showing us with the data analysis, I think is mainly by stability. To what extent can you say that this biostability also or always implies tipping points with their characteristic poor reversibility, etc.? Are these the same, or are the conditions where biostability might actually mean the system can actually flip pretty quickly between two stable states?
Yes, great question on early warning. So a simple answer would be where you have systems that have got their own longer timescales, oceans, ice systems, presuming that you detected the tipping point was still far enough away, there certainly would be potential to imagine that a concerted mitigation could prevent you crossing it. When it comes to some faster systems, monsoons that may be being disrupted perhaps more by aerosol pollution locally than by the large-scale warming trend, then you have the advantage that that these are short-lived radiative forcing agents and that you might be able to alter their inputs quite quickly with effective policy. But clearly in some cases, the early warning, I think of it more as an aid to adaptation. Now, there may be cases where we get a warning, and in fact, you could say, and Ricardo was kind of telling us, that we've had some possible detections of having passed some tipping points in Antarctica and possibly Greenland already. We're not in a position to stop the tipping point there. I still think there are management options which we could discuss to limit the rate at which to see that the resulting sea level rise would ensue. But I would still say that forewarned is forearmed. So if we knew something very bad was coming, even if we couldn't stop it happening, we know how much that we have considerable adaptive capacity, depending on the nature of the event, to reduce the impacts and the vulnerability or exposure we have to that. So that's classic risk management, and I think we might be applying that in the climate sphere as much as we do in other spheres. Thanks.
Thank you, Bart. Regarding the biostability, the thing is that biostability means that for the same conditions, you can have two alternative states, right? So what I mean by showing that picture is that if you push the system toward a tipping point, but not necessarily the tipping point in the conditions of seasonality, meaning annual precipitation and fire, if you cross that, you can flip to a different state. So this means that you can have a different configuration of the system by having bioinstability. It depends on how you push your system towards the other state, or you increase resilience to stay in the same state you were before.
Okay, I have two questions here and two questions over there. Okay,
my question is again for Tim. Colin Pritchard, Edinburgh University. Hi, Tim. Thank you very much for your very cogent explanation. I would basically agree with you on geoengineering, except may I infer that you prefer an enormous global scale, uncontrolled experiment in geoengineering as opposed to a small scale, uncontrolled one. At the moment we are in the former. And it seems to be a little bizarre to prefer the former to the latter.
I'm certainly not preferring carrying on with our current uncontrolled experiment. And I'm not, what's the right word? I'm not monolithically set against things that are being discussed under the banner of geoengineering. So it's quite a nuanced, I think that's quite a nuanced discussion to have, perhaps over lunch, because it really depends on the options you're considering. So you've got some things which would be reflective roofs and road surfaces that are very practical local adaptation options against urban heat islands that, if you did it on a large enough scale, could have some measurable effect on regional climate, and I think are very sensible. So we have to I think we have to be nuanced on specific proposals, specific technologies, but I think we can perhaps all agree that we certainly, none of us want to continue the current uncontrolled experiment. I guess knowing the numbers, we realize that we would like the strongest mitigation efforts possible, but we now know that some additional things, including carbon removal from the atmosphere, we may want to develop that capability because we may need it as a part of the risk management portfolio.
Okay.
My question goes to Marina. Concerning the analysis you made, I would like to know if you consider only intra-ecosystem or if you also integrate the inputs of changes in the surrounding ecosystems. For example, we all know that the Atlantic forest is going to very strong transformation in biodiversity, land use, and etc. And I would like to know if you have, if you are also working on the impacts of these changes on the Cerrado.
Yeah, thank you. Regarding the Atlantic forest, we haven't been studying this border with the Cerrado yet, but we want to expand. What we've been studying is just the Cerrado and the forest transition and the borders within. So including heterogeneities within forest and within the Cerrado, because it's known that there are three forest species within the Cerrado and three savanna species within the forest. So we are just studying these interactions within, not in the boundaries with Atlantic forest, not yet.
Okay, thank you.
My name. Okay. Jim, you mentioned the Pacific Decadal Oscillation is approaching a tipping point. What will happen when we reach that point? And Ricardo, you mentioned that we have passed the tipping point at Amundsen Sea. What will happen to, how can we see it in the near future? Will the glacier move faster in the next years? Will we see more icebergs due to the past tipping point?
Thanks. I should definitely clarify on that point. So what I'm showing is there's slowing down in the sea surface temperature fluctuations in the North Pacific and in the index. You could view that as a shallowing of the valley, but that doesn't mean that there's some other valley that's available to tip to. We don't have a conceptual model for that. What we have done in that work is look quite carefully about whether there's a simple physical mechanism for why would the sea surface temperature fluctuations be slowing down. And at least part of that can be explained by the limited observations we have that the mixed layer, the surface layer of the ocean has been getting deeper, at least in the last 50 years, with strengthening of winds in the North Pacific. That means you have a bigger heat capacity. You perturb its temperature by a given amount, it's going to recover from that perturbation slower because it's a bigger heat capacity. So that's why I took the story in the direction of the ecosystems. I'm not at all sure whether I can even conceptualize a tipping of the North Pacific climate. Maybe others can. But what's key is even if you just accept the observational signal of the slowing down of the surface ocean fluctuations, that matters for the ecosystems. And we've seen abrupt shifts in North Pacific ecosystems. They're well documented. In fact, that's where the PDO index originally came from. One inference you could make from the analysis of the observations of the slowing down over the last century is that the likelihood of such abrupt shifts and large amplitude shifts of the ecosystem should have gone up according to very simple models. And we certainly did see some abrupt ecosystem shifts.
Concerning the question on the Amundsen Sea Basin, so the observations that I showed earlier, those are from satellite images showing that over the past decades, actually, these glaciers in the Amundsen Sea Basin have sped up. So this is, that they have been speeding up, this is no news from the last year, but it's been observed over a while now. But there are a number of observations, so satellite observations, but also direct measurements showing that these glaciers have been speeding up. So the variables that we want to look to in the future would be surface velocity, of course, ice flux, but also the change in the surface elevation, because that will tell us when the ice sheet or that particular part of the ice sheet actually retreats into that deep valley, the subglacial troughs, basically, that are important for this kind of instability. So those are the variables that we want to be looking at in the future.
Okay, thank you. And our last question.
Thank you, and thank you for some interesting talks. First of all, a comment to the previous questioner who asked about aerosols. If you're concerned about aerosols, I would suggest you're probably not concerned enough. And I have a paper this afternoon at UPMC and tomorrow evening as a poster, which you might be interested in. My question really is about aerosols. The whole focus of what we've been talking about is about the greenhouse gases, but it's relatively easy to show that the aerosols passed a tipping point decades ago in many areas of the world, like Southeast Asia, West Africa, and many others. How much work have any of you done on assessing the effects of these continental scale aerosol plumes, which didn't exist 50 years ago and which now exist in 8 places in the world? The IPCC in the AR4 said that aerosols may affect the hydrologic cycle and the global circulation systems more than the greenhouse gases. I think they're right. In fact, I know they're right. How has that been incorporated into any of the work you've done? Thank you.
I've done some work on the aerosols. I certainly considered it as an important forcing factor for some of our candidate tipping elements, especially monsoon systems, including Indian summer monsoon, where there's observational data showing, at least correlational data showing a strong link between the increasing atmospheric brown cloud of aerosols and overall decline in rainfall, effects on crop yields, delay of monsoon onset. So we always said in our tipping elements analysis that if there were a threat to these subtropical monsoon systems, it was the more immediate or apparent threat was from the aerosol pollution. And I think that's a subject that continues to deserve more attention in China, even in West Africa and other regions. So we do take that seriously. And I suppose the flip side, good news, is it's if there's potential to more quickly control the aerosol pollution.
Okay, I would like to thank again all the presenters for their excellent presentations, and thank to the audience for the contributions. Thank you very much.